It's my pleasure to get the chance to talk to you about self-testing. This is a topic that I've recently been working quite a bit on together with several people here at the University of Copenhagen. So let me first try to convey this general idea of self-testing. And please feel free to stop me at any point and ask questions. I prefer that over you waiting till the very end. Okay, I want to start with this warm-up example. So imagine that we have this situation where we have a box. And we think that within this box, this box hides a quantum state psi. And whenever we press a button of this box, we have like several different buttons to choose from. And say this X describes which button we are pressing, think that it's a number from 1 to n. And then this box provides us with some, again, labeled output A from some finite set, right? And then we know that what this box is doing, it's measuring some quantum state, psi. So quantum state is described by a unit vector and some complex d-dimensional space. And then this X kind of selects a measurement. And measurement we specify by its so-called POVM elements. So these would be positive sum-definite matrices that add up to identity if we sum over these outcomes. Now, if we know the state and we know the measurement that we have selected, then we can use postulates of quantum mechanics to calculate the expected probability to observe the outcome A, given that we have input this little X, so selected measurement X for this box to perform. And this probability would be given by this inner product. So kind of, I'm using bras and cats to denote row and column vectors, respectively. All right, but now we might want to solve the inverse problem, right? Now suppose that you don't know what this box hides, and you have a question mark on this box. And instead you ask, okay, if I only see this probability distribution P of A given X, how do can I recover the state psi and the measurements as given by these positive sum-definite operators that gave rise to this probability distribution? Okay, so, and it turns out that in this setting, it's actually impossible to solve this inverse problem because there could be many different states that I'm measuring that give rise to the same probability distribution. Or if we kind of try to distinguish quantum devices from classical, then I could say, oh, inside this box, it could be a purely classical device because, for instance, I'm not putting any limitations on the time that's needed to produce this probability distribution. Okay, so now that we see like kind of that in this single input, single output case, this inverse problem is not solvable, then it's perhaps surprising that if we now, rather than just focusing on one box, we take kind of two different boxes and the so-called two-party Bell scenario, right? So now I have two boxes, A and B, and in each one of them, I can select this measurement. So X and Y respectively, and they provide me these answers A and B. And in this setting, sometimes we can solve this inverse problem. Okay, but first let's kind of talk about how the white box situation looks. Okay, so I have a two-party Bell scenario. So here I kind of have these two physics, speaking from the physics side, that would be two labs, so Alice and Bob, and in each one of them, I could do some set of measurements. So these AXAs now are measurements on Alice's system, and BYBs are measurements. So these positive sum-definite operators adding up to identity on Bob's system, right? So I select which measurement I'm doing in Alice, X, and which on Bob, Y. And then again, if I know the state that's being measured, then I can use the rules of quantum mechanics to tell me that, well, the probability that I'm going to observe outcome A from Alice and B from Bob, given that I input in these boxes X and Y, so selected these measurements X and Y, is given by this input. Okay, and so I take a tensor product with Alice and Bob's these positive sum-definite matrices here. All right, and so kind of at a very high level, I would say that self-testing happens when seeing this joint conditional probability distribution P allows me to infer this what I call a quantum mechanical description of these boxes. Namely, I can figure out what is the state that Alice and Bob measured and with what measurement. Okay. And so when we talk about self-testing, then it depends what, it can vary what precise classical observations do I need. So one option would be that I can see this entire set of, or I assume that I know the entire set of these numbers, these probabilities, A, B given X, Y. So this is often referred to as correlation. So I know all of these numbers, P, A, B given X, Y. But sometimes I actually don't need to know all these numbers, and it suffices for me to know some functional evaluated on these numbers. So in that case, we would talk about winning probability of a non-local game. So I can self-test just from a single number rather than a collection of numbers. Okay. But before, so since we are now to non-local games, let me give you an example of a non-local game, and this will also be useful in the counterexamples that we will construct. So this is a very well-known game. It's called Magic Square Game. And here we should think of this 3x3 grid and think that in every entry, these CIJs, they should be numbers plus or minus 1. Okay. And the way I play my game is that I ask Alice and Bob to fill in one of the rows or one of the columns. Okay, so this is row 1, row 2, column 1, column 2, column 3. Okay? And then as the answer, they provide a filling of that row. So a plus minus 1 string of length 3. Right? Every row and column has 3 numbers. All right, let's say I ask each of these questions, rows and columns, with uniform probability. And now what are the rules that allow Alice and Bob to win? What they need to satisfy in order to win. So there are 2 rules. One is the parity rule, namely that along every row and column, the numbers should multiply to +1, except for this very last one where they should multiply to -1. That's the parity rule. Now, consistency rule says that if Alice's and Bob's questions intersect in some square, then they should assign the same number. Okay, let's think about this generic case where one person is asked a row and another person is asked a column, right? They intersect every one square, and the consistency rule then would ask that the number assigned on that square is the same. All right, if Alice and Bob satisfy both of these rules, then they win, and otherwise they lose. Okay, so we can take a look at an example. Maybe we ask Alice to fill in the first row, and we ask Bob to fill in the last column. Okay, so and maybe this is these are the answers that they provided, and to see that they win, we need to check the parity rule. So it needs to be even or multiply to +1 for Alice. Indeed, it does, and it needs to be odd, right? Because Bob got the special last column where it needs to be multiplied to -1. That checks out. And final thing we need to check is that at the intersection, they both assign the same thing. So they assign +1, both of them. Because both of these rules are met, so they win this game, or this round of a game. Now, it turns out that it's not possible to always win this game. So what I mean by always is that Alice and Bob could win irrespective of which question and answer, which pair of questions we asked them. If we use what's called like a deterministic strategy. And so that would be some kind of function that tells Alice and Bob what should they answer if they are asked a specific row or column. And then it comes down to the fact that if I try to fill the impossibility to win kind of classically, so without quantum resources, comes down to the fact that if I wanted to fill in this square with plus and minus 1s, so that all these parity checks are met, then this is impossible. You can see the impossibility by multiplying together the row sums versus the column sums, column products, right? You get a +1 in one case and -1 in that. All right, but now quantumly we can win this game irrespective of of the pair of questions selected. And in this case, the ability of the quantum players to win kind of hinges on the possibility to fill in this 3x3 grid with operators, so that along every row they multiply, along every row and column they multiply to plus identity while multiplying to minus identity on this last column. Okay, so I'm not going to go into details why this is what is needed, but that is what in the end it comes down to. Okay. I see that there is a hand.
Laura, in the previous slide, you described a measurement as a POVM, and now you filled the entries with these observables. Is there an easy way to explain where the POVMs come from once you have this?
Actually, you're completely right in calling me out. I'm just picking and choosing my representation of measurements as it pleases me. So this is the so-called observable representation. And then if you want to go to this POVM picture, you just take the projections onto the plus and minus eigenspaces.
And row 1 has 3 eigenspaces,
so there's an additional thing that didn't mention. Very good catch. So the requirement is that actually along every row and column. So also I'm omitting a tensor product here. So there's X tensor identity, right? Z tensor 1 and things like that. So this is a 4x4 matrix in every little square. Along every row and column, so within the same row or column, these operators, they commute. Okay, so what that means is I can simultaneously diagonalize them. And kind of what I do then, I measure in this diagonal eigenbasis. So I take the projections onto the basis vectors that for the basis that simultaneously diagonalize that row or column. Does that make sense?
Yes, the last step is the part where I'm lost. Why is the center one, Z tensor 1, associated to a particular eigenspace of Z tensor 1?
Sorry, can you say that again?
So for example, in the center column, you have Z tensor 1, and then you're saying that there's an eigenspace there. I understand that the rows are simultaneously diagonalizable, the columns are simultaneously diagonalizable, and that must be some eigenspace that the two commutative subalgebras have in common. But why is that labeled Z tensor 1 and not labeled by the eigenspace? I'm sorry, I'm just...
Sorry, I don't mean eigenspace. I mean eigen. So
the projection.
I pick a basis in which, say, the operators in the second row are all diagonal. So when Alice is asked to perform measurement for second row, she measures in that basis. And from the basis information, right? So every one of those basis elements will be a plus or minus 1 eigenvector for each of the 3 operators. And then that's the plus minus 1 string of length 3 that she responds.
Okay. So the Z tensor 1 in the center tells me what eigenvalue to put in that entry in my response.
Yes.
Okay. It's not a projection. Okay. Thank you.
Yes. Okay. All right. So there is this kind of small strategy, quantum strategy that allows us to small. I mean, you don't need kind of high dimensional quantum states. The local dimension for Alice and Bob is just 4. Okay. So the kind of intuitive idea of this self-testing was that we wanted to infer quantum mechanical description. So this strategy, these some kind of description of measurements together with the state from classical observations. So an informal self-testing statement for magic square game would look as follows. It would say that if you have a perfect strategy, so the strategy S, I think of it as a triple state, together with operators for Alice and operators for Bob. So the strategy is a perfect strategy for if you have a perfect strategy for magic square, then it is essentially this strategy that we just saw. Okay. Now all the details I'm hiding behind the word essentially. All right. So let me ease you towards what do I mean by essentially. So we have this, by the way, can you see my cursor, or I'm just pointing for myself? Okay, perfect, thank you. So let's look at this strategy as tilde for this two-party bell scenario. Right? So we don't see the strategy itself, we don't see the orange stuff, but we assume that we know this P tilde that it generates. When can we infer S tilde from P tilde? Well, if there is some sort of transformation that we can do on S tilde that leaves P tilde unchanged, then of course we won't be able to discern those two different strategies, right? And I want to point out that there are two different manipulations that you can do to S tilde that leave this P tilde unchanged. Okay, so the best we can do is kind of only identify the strategy up to these transformations. Now, the first transformation that you can do is you can locally change the basis for Alice and Bob. Okay? So kind of more formally, it would look like that I'm applying some unitaries UA tensor UB on my state, and then I've conjugated my measurement operators with the same unitary. And when you compute what is the correlation that this generates, then kind of U cancels out with its dagger. Right? And you get with the same correlation as was generated by this strategy S tilde. So change of local basis, that's one thing that we can always do and that we cannot detect from this P tilde. Another thing that we can do is we can attach another state. We can give, in addition to this psi tilde, we give Alice and Bob some other state as well, but then we don't do anything on that state. Right? Again, mathematically, we just tensor identity onto those operators. And again, if you calculate the generated correlation, then this auxiliary state just goes away. So you're left with the same correlation as the one generated by the tilde. All right. Now, with these two things in mind, we're going to define this notion of a local dilation. Okay. All right, so here we have two strategies that are triples. We have strategy S and S tilde, and we say that S can be locally dilated to S tilde, and we denote it via this arrow notation. If I can find two isometries, UA and UB, so think of this as active on Alice, this active on Bob, so that if I apply my measurement operators from the strategy S onto the state, then that's up to this local isometry. It's the same as the action of these tilde operators on the tilde state. Tensor some auxiliary state on which I'm acting trivially with identity. So this is kind of the key equation, I would say, for self-testing. Okay. I know it's a little bit technical. Maybe we can try to develop a little bit of intuition by observing, making this simple observation. That now, if I fix X and Y, and I sum over little a and little b, this equation, then I'm taking this summation here, and remember that kind of A's were my outcomes, and because this is a measurement, that if I sum over A, I'm going to get identity, and the same here, right? So what's going to happen is these operators are going to go away, and I'm going to be left with just this equation. All right. And so in self-testing, so this kind of second equation is weaker than the first one. And in some cases, it happens that we maybe cannot infer the full description, the full strategy that our black box is hiding, but maybe we can still infer like what is the state that is being measured. So here we're saying that, oh, we can infer both state and measurement, but here we can only infer the state. So another kind of simple but later on useful observation is that if we have I can dilate some strategy S to S tilde, then they generate the same correlation. Essentially, when you take inner product between the left-hand sides of these two equations and the right-hand sides of these two equations, right, you see that these isometries, they're going to cancel out. So you, on the left-hand side, you'll get the correlation generated by strategy S, while on the right-hand side, the one generated by S tilde. Okay, so now with this local dilation, we can state self-testing as follows. So we say that the gain G self-test strategy S tilde, if for any optimal strategy S, you can dilate it to this canonical strategy S tilde. Right? And this is the precise sense in which a magic square self-tests that strategy that I showed. Right now, kind of a variant of self-testing that is practically applicable is the so-called robust self-testing. So, because that allows us to apply this concept in situations where we have noise and where we actually don't know this correlation or this gain value that our strategy is achieving perfectly. And this is the realistic set. Right, so we say that gain G robustly self-tests S tilde if for every epsilon, so I think that epsilon is this desired closeness of your actual strategy to the canonical one, there exists a delta. This delta is like the closeness of your classical observations, so that for any delta optimal strategy S, so this strategy S should win gain G with probability that's at most delta different from the optimal, you can now epsilon dilate this strategy S to S tilde. What does this arrow with an epsilon mean? Well, you just take this definition of local dilation and that you say there exists isometry so that this equation holds up to epsilon, right? So these are two vectors and you want that they are close, let's say 2 1. Like the difference has 2 norm at most epsilon. Okay, any questions about this kind of more formal definition of self-testing? Okay. All right. So here are the questions that kind of motivated our work with Simone. So the first one, we wanted to ask, okay, if we have some, so even though it seems like self-testing is something that we are after, that we want to find, it seemed like, oh, anywhere you look, any interesting example of game that's exhibiting quantum advantage. So no matter which such interesting game you look at, you can prove that it self-tests the strategy that you had in mind, right? So somehow it looked like self-testing is everywhere. So that's what we asked. Is it indeed the case that every game self-tests its optimal strategy? And the second question we wanted to ask, well, is every self-test also robust? And here, again, it seemed like every time you have some argument that shows that the given scenario was a self-test, that if you just kind of try to insert epsilons in your argument and apply some Cauchy-Schwarzes, then you manage to show that it is also a robust self-test. Right? And if the answer was yes to this question, then it would be very nice because it's much easier, of course, to prove that something is an exact self-test. And then this robustness would just follow quickly. Okay, so the first thing I want to now say regards this question 1. So does every game G self-test its optimal strategy S tilde? So actually, even before we started our work, we knew that the answer to this question is no, right? Well, before we started our work, we only knew one such game, and that was given in this work by Tsui et al. And they call it glued magic square. So what you do here is, again, you are going to ask, so it's works very similar to the magic square game that I explained before. So again, think that Alice and Bob get these rows or columns as questions. And then in order to win, they need to they need to meet these parity conditions and consistency conditions. So here, notice that kind of this non-trivial column is here, this third column, and it's has length 6 rather than just 2. Right? And here we want them to multiply to minus. Okay. So this is also a game that you can win perfectly quantumly, but you can't win it perfectly classically. And you can see that you can build a perfect quantum strategy for this game from a strategy of magic square. Okay, so what would you do? What Alistair and Bob would do is they would say, one way to do this is you can play magic square on this top square, but if you are asked anything from the bottom square, you just answer +1 always, like to all these D variables, you just assign +1, right? So that will be one way for Alice and Bob to win this glued magic square game. But now, of course, you have kind of the complementary strategy where you play magic square on the bottom square, and then you answer trivially on the top square. All right. So notice that kind of these two strategies, they don't generate the same correlation. Why? Because one of these strategies always has like 0 probability of ever answering any -1 down here, while the other strategy has 0 probability of ever answering any -1, assigning -1 to any of these C variables. So they don't generate the same correlation, and therefore they cannot be locally dilated to the same strategy. Okay? So that shows that glued magic square is not a self-test. Okay, yeah, I have that written down here, but let's go further on. However, what it turns out that it's still, so it doesn't self-test this full strategy, the operator, the measurement operators. However, in some precise sense, one can show that these two strategies I just told you are essentially the only ones, right? So now you don't have a single optimal strategy, but kind of two inequivalent ones. And they both use the same state. They use the same state as the magic square. Right, so this glued magic square game still self-tests a state in this maximally entangled state in dimension 4. Okay, so we update our question, right? We're just going to ask if every game with a quantum advantage self-tests its optimal state cycle. Okay, and we are going to answer, so both of these questions. So is every self-test robust, and does every game self-test quantum state in the negative? And to get these examples, we can use the same construction. So we call this the OR game. Let me show you how to define an OR of two games. So here we have G1 and G2, and this is going to be my notation for the OR game. What are the questions? What are the answers? And what is the winning condition? So Alice and Bob now are going to get a pair of questions. Think of the first question as being from the first game and the second question from the second. Similarly to Bob, Y1 from the first game, Y2 from the second. And then what Alice and Bob essentially need to do is they need to choose which game they're going to play. So Alice needs to say, oh, I'm going to play game I. So I is 1 or 2, and then give an answer for that game. Okay? And Bob does the same. Now, in order to win, we want that I is equal to J. So Alice and Bob chose to play the same game. And then once they are playing the same game, then you can require that they win that game. These answers A and B win that game that Alice and Bob chose to play. Any questions about how the game is defined? Okay, so now let's make this very simple observation that's again going to be useful later on. So suppose that the games that you took an OR off, you can win them perfectly with some quantum strategies, right? They have some perfect strategy that wins probability 1 S1 in game G1, and also a strategy that perfectly wins your second game G2, right? Then these two strategies S1 and S2 can be promoted to strategies for the OR game G1 or G2, right? Where the players always choose to answer from game number 1 in the case of S1, or always choose to answer from game 2 in the case of S2. And these two will give rise to two different perfect strategies for this OR game, right? Because for the first strategy, your I and J will always be 1, but in the second, it will always be 2. Okay. All right. So now, let me show you how to get an OR game that does not self-test any state. Right, so this will show that the answer to this modified question number 1 is negative. So I'm going to take OR game of two appropriately chosen games, and it's not too important what exactly I'm taking. There's going to be just one property that I'm going to be using of these games, and I'll highlight that. So for G1, I'm just going to take magic square, I showed you in the beginning, and for G2, I want it to be a game that has a perfect strategy that uses a state in dimension 3, right? For instance, I can get such a game by considering the so-called Cohen-Spector sets and then taking the game version of a Cohen-Spector set. All right, now the important property that I'm going to use is that the fact that the local dimension of this entangled state used in these two games, that is co-prime. So in the case of magic square, the local dimension is 4, and for this G2, the local dimension is 3. And 3 and 4 are co-prime. Okay, so what do? We take an OR game, and then we observe that because G1 and G2 have these perfect strategies S1 and S2, then I can also get a strategy for G1 or G2 that have local dimension 3 and 4 respectively. And now for contradiction, we're going to assume that this OR game is a self-test. Well, what does it mean? It means that I should be able to locally dilate each perfect strategy to some fixed strategy S tilde. Okay, so I can locally dilate S1 to S tilde, and also I can locally dilate S2 to S tilde for some S tilde. So what does it mean that I can locally make this local dilation? Well, it meant that I can find these isometries, right? So that I conjugate it, so that I apply them to the state, then I get my canonical state, psi tilde, tensor some other state. Okay, now what do? Is I take a rank, the Schmidt rank on both sides of this equation, and I observe that my local unitaries cannot change the Schmidt rank. Okay, so that means that the Schmidt rank on the right-hand side is equal to the Schmidt rank of the state psi I. Now, both of these states, the psi tilde and the auxiliary state, they are states between Alice and Bob. And when I'm talking about Schmidt rank, I'm kind of looking at this partition between Alice and Bob. So to get the Schmidt rank on the right-hand side, I just need to take the product of the Schmidt rank of psi tilde and times the Schmidt rank of this auxiliary state. Now, because this game is like you can't win it classically, this psi tilde has Schmidt rank. You need to use some entanglement, so your dimension cannot be 1. So that means this rank is strictly greater than 1. So what you see here is that the Schmidt ranks of the two states, they have a common divisor, a common non-trivial divisor R tilde. Okay? But the two Schmidt ranks were 3 and 4. Right? These were these local dimensions. So that's impossible. That's where I get my contradiction. Because 3 and 4 do not have a common divisor. Any questions here? Maybe a question could be, what is Schmidt ring?
One question, could you please repeat that thinking where you mentioned that two states have to share a common divisor for the Schmidt ring?
Yeah.
Okay.
Okay. So I'm assuming that S1 can be locally dilated to S tilde and S2 can be locally dilated to S tilde. In particular, actually, I'm just assuming it for the state. So that means that I can find an isometry. So like I need two local isometries, one for one and one for two, so that this equation holds. Okay, and now I'm going to argue about the Schmidt ring of the two sides. Okay, so the local isometries, they don't change the Schmidt ring. And therefore, I get that the Schmidt rank of psi I must be equal to the Schmidt rank of the right-hand side, because the application of these local isometries didn't change the Schmidt rank of psi I. All right, now I look at the right-hand side and I say, well, the Schmidt rank, because what I'm looking at is Alice-Bob partition. And this psi tilde is shared between Alice and Bob, and this state is also shared between Alice and Bob. But then I have a tensor product here. So the Schmidt rank of this tensor product is just the product of the Schmidt ranks. So that's how I get the Schmidt rank of this state psi tilde times the Schmidt rank of this auxiliary state. And then I say, well, the Schmidt rank of this is not one. It has to be greater than one. And then I get that both of these, so the rank of psi 1 and the rank of psi 2, they have a common non-trivial divisor, namely this arc tilde. And that's my contradiction, because rank of psi 1 is 4 and rank of psi 2 is 3.
Thank you.
Okay. All right. So the second counterexample is this non-robust self-test. All right. And again, the precise gains that we use are not important, just some. So the property here that we relied on was this co-prime dimension. That was the only thing that mattered. And here again, it's just going to be some properties about these gains that matter. So for G1, I want to take a gain that has a perfect quantum strategy, so a strategy that wins with probability 1, and that is also a self-test. For example, we could take magic square gain again. Now G2, we need a more exotic gain. So here I want a gain whose quantum value is equal to 1, but that does not have a perfect quantum strategy. So what does this mean? So this quantum value, so the highest quantum success probability, is defined as the supremum over all quantumly attainable winning probabilities. Okay? And somehow the quantum set is not so well behaved, so the supremum is not always attained. And that's a type of a gain that I need that exhibits this non-attainment. Right? So if I take the supremum, then I get 1 perfect success, but actually I cannot hit exactly this perfect success probability with any quantum strategy. All right. So why does this work? So I want a non-robust self-test. So I need 2 things. I need to argue that this OR gain, that it is a self-test of some strategy, and then I need to argue that it is not a robust self-test of that strategy. Right. So point number 1 is that this OR gain here is a self-test of strategy S1 tilde, which I just take it to be the strategy of this canonical strategy of magic square gain, as when seen as a strategy in the orbit. Why does it work? Well, if I have a strategy S that achieves perfect success, so it achieves perfect success in my OR gain, then because this gain G2, it does not have any perfect quantum strategy. It turns out that Alice and Bob always actually need to play this game G1. Right? There's some argument that says, so Bob will always need to play G. All right, but now G1 is a self-test, right? So that means this perfect strategy S is also a perfect strategy for G1, and G1 is a self-test, so I can map this S to this canonical strategy for G. And so that's the basic idea of why G is a self-test. If I want to play the OR game perfectly, because G2 does not have a perfect strategy, then I always need to play G1. Right. Well, why is this not a robust self-test of this strategy S1 tilde? And now this game G2 comes into play. Okay. So remember that the quantum value of G2 is equal to 1. So that means that for every delta, I can find a strategy S delta that wins this game G2 with probability 1 minus delta, so arbitrarily close to 1. All right, now if I think of these strategies as strategies for the OR game, right, then these strategies only output answers from game G2. Okay. So the probability distribution that they produce, they never get close to that of the strategy for this strategy S1 tilde, because this S1 tilde only outputs answers from game G1. And therefore, I cannot locally dilate them to something that is close. That's kind of the basic. Okay. Any questions about this other example? All right. Okay, if not, then let me show you kind of some open questions. So here's kind of a table of what's known in terms of counterexamples to self-testing. Right? You could ask, oh, do I have a counterexample of a game that does not self-test anything, or counterexample of a game that is a non-robust self-test, so that it is an exact self-test, not a robust one. And then you could ask the same one for extreme quantum correlation, truly quantum correlation, right? And then we provided these counterexamples for non-local games, but then the same question is still open when it comes to correlations, right? So that if you were self-testing from a correlation and you have an extreme quantum correlation, is it necessarily a self-test of some state? Or is every exact self-test also robust? And so our examples, they don't provide such correlations, basically because you can use two different strategies with different correlations to win this OR game. Right? That's what our arguments hinge on. Okay, yeah.
What are the extreme correlations?
So you could look at, so if you look at this two-party Bell scenario, right, you have this correlation, that's this joint conditional probability distribution, P of AB given XY. And then you ask, okay, what is the set of all PAB XYs that can be generated by some state in some measurement? Let's say you fix the number of questions and answers, right? So this is a convex set. This is called the set of quantum correlation. And you can talk about points being extreme in this set.
Okay.
Right? And somehow we think that maybe we can only self-test the extreme points in this correlation. That's why I raised this question for extreme. Okay, and maybe then an additional open question beyond these two question marks would be, somehow it seems like for some statements in self-testing to go through, we need to make an assumption that correlation is extreme, but then I don't know how to check it. Like, so, and maybe checking in general is very hard, but could there be some nice sufficient conditions, easily checkable sufficient conditions that would allow me to certify that the given quantum correlation is indeed extreme? All right, thank you. As for the things I wanted to tell you, I'd like to stop here, but I'm very happy to discuss any questions you have.
Thank you very much for your talk. Was very interesting.
On this last, is convex set polyhedral? I guess I mean one certificate of being extreme would be a supporting hyperplane even for any convex set, right? You don't know how to check if something's a hyperplane, but is that set of correlations polyhedral?
So I mean there are like points that are not exposed. So I'm sorry for my ignorance. What does it mean to be polyhedral?
Just sort of a finite number of sides instead.
No,
of,
they're not finite
sure.
number.
Okay.
No. This set is somehow very. It has some like round bits and then non-exposed points. Yeah.
Thank you.
Any other questions? Okay, also had the question. So what are the applications of this? Can it be used somewhere in cryptography? Maybe when you can eavesdrop on somebody's game or something and try to use the strategy or
Yeah, like I think the way that people initially motivated is by saying, oh, it's somehow well, you could say maybe you want to know someone somehow tells you, oh, they give you some box and say, oh, this box prepares this quantum state. Know that it prepares this quantum state, right? Or that, oh, here you have another measurement box that performs this quantum measurement. How do you know that it actually does that? And so self-testing is a way that we can address this question in a somehow the most paranoid scenario where you don't have any trusted quantum devices. So if you just wanted to know, like, that your measurement or state generation box produces the correct state and you have trusted measurements, and you can measure using your trusted measurements and check, is this the statistics somehow correct, right? But if you don't have trusted measurement nor state generation boxes, then it's somehow like chicken and egg sort of problem. It could be, sometimes I use this analogy. I say, oh, imagine that you have an untrusted scale and an untrusted block of weight that someone claims that it weighs 1 kilogram. How do you certify that your scale works properly and that this block really weighs 1 kilogram without having any trusted kind of reference? But then somehow, so that's somehow like some more philosophical or cryptographic, whatever motivation. But recently, kind of these self-testing techniques, they are just used a lot in complexity, quantum complexity theoretic proofs. Like they are used just as a proof ingredient. You want to say, oh, I have some, like, because they somehow allow you to tell, oh, what could have generated some classical, some probability distribution, right? They somehow give a very tight description of what could the state and the measurements be, and that is sometimes useful in proofs. For instance, in this MIP star equals RE paper, right? Also self-testing is used.
Yeah. If there are no more questions, let's thank the speaker again. Oh, good.
One extremely basic question, embarrassingly simple. what kinds of quantum games are people looking for now? So you mentioned Slofstro's game, right, where you can get within epsilon, but there's no perfect strategy. Are people interested in particular qualities of quantum games, or is there enough? Is there enough variety around for the types of theorems you're seeking to prove?
I'm not. Can you elaborate? I'm not sure I fully understand.
I'm just asking a very basic question. What is current research like in quantum games and vis-a-vis just creating games? Do people look for three-party games or games with different kinds of shared states? What are the parameters that people are playing with as they create quantum games?
I think it's definitely true that somehow for two-party games now we have a better understanding than what we did. I think kind of like nice classes of structured games with like quantum advantage. To me, okay, take it with a grain of salt, just because I really like nonlocal games. To me, it's still interesting. Maybe just like having a single game with a quantum advantage that's not super interesting unless you have some very good motivation. I don't know. I'm interested in kind of, so now we kind of know that, oh, in the worst case, things are very complicated. And I'm interested to kind of know when are things easy for these nonlocal games. Like when can I compute things, like compute the entangled value, or what are the conditions that would enable me to do that?
Thank you.